Hi, my name is Valerie Varan. I'm a licensed professional counselor, a holistic life coach, and an advocate for quantum psychology. With me today is Doug Matzke, and I am so excited for us to talk. Let me read you a little bit about Doug. So, Dr. Matzke is a prolific scientist, researcher, and presenter in his areas of expertise about limits of computation, hyperdimensional mathematics, neurocomputing, quantum computing, real intelligence, and metaphysics. During his 45-year career, he was chairman of two SciComm 1992-1994 workshops, contributed to 15 disclosed patents, with 8 granted, has published more than 50 papers and presentations, and earned a PhD in quantum computing. Doug has adopted the moniker of Quantum Doug because he combines these deep reality subjects as the source science beneath his quantum mind-based model of humanity. Welcome, Doug.
Hey, thanks. It's so great to be talking with you the last couple of weeks and to hang out with you tonight.
Oh, I'm so happy. Doug, you've been so gracious to agree to entertain a bunch of these questions that I wanted to pose to you. I know we both have in common this idea of getting people to understand more about the quantum mind. So buckle your seatbelts, folks, because we're about ready to talk about a lot of things. Let me read you some of these things we're going to be talking about. So we're going to have a scientific basis for the quantum mind, spiritual and non-ordinary experiences, spiritual light bodies, even orbs, experience of past and future events, telepathy, levitation, telepathy, bilocation, teleportation, mind matter effects, and even law of attraction. So Doug, you begin your book, Deep Reality. I'm going to show everybody what that looks like. I definitely encourage people to get your book. And you begin Deep Reality by explaining how the distinction between what we call physical and non-physical is really not so useful anymore. And we and all things have been shown to be a wave-particle duality. Fundamentally, particles are quantum waves. And this is actually the basis of all quantum physics. So in explaining your quantum mind, information-oriented reality source science model, you do seem to distinguish physical reality, which you have reminded us is space, time, mass, energy, electromagnetism. And even when we talk about waves and frequencies and fields, it's space-time talk. And I'm so glad you're helping us distinguish that.
Yep.
And you're helping us distinguish it from quantum reality, which is more about quantum field theory, quantum waves, quantum wave probability amplitudes, which we'll talk more about the significance of that later. Superposition of states, nonlocality, entanglement, key terms for understanding what we talk about when we even talk about the word quantum. And then you're helping us even go deeper than that. And you've really been a teacher for me on this one. So this even more primitive reality is based on bits of information and is this more protobit physics, as you call it, aspect to reality that you see as really creating the structure for the quantum reality beyond space-time and ultimately our normal reality of physical space-time as well. So on page 51, I love this. And for our viewers, I'm going to kind of give you a synopsis of what Doug wants to teach us because it's pretty heady. And by my giving this more simplified introduction to what he's about, as we back up and start more simply and then work our way towards these subjects, I think all the viewers, you guys will understand Doug a lot better. So on page 51, I love where you simplify and you say this: bits can be naturally combined to form structures, such as qubits, ebits, photons, particles, rotes of meaning, and even thoughts. Each bit mathematically represents a separate, tiny, protodimensional. It's orthogonal, meaning 90 degrees to all others. And then you go on to describe bits in terms of scalar states, like regular counting numbers, which have magnitude, vector states, which have magnitude and direction, and which can be added as concurrent states and multiplied as changes or operations to those states. And of course, that's where you go deep into the math. But you propose that these bit dimension vectors combine to form the geometric precursors of the quantum particles and of space-time electromagnetic energy and mass particles. Now, prototime, which I'm going to tell our viewers, is about change. It's not time as we know it, it's about change. And ultimately, you show how it might even could give rise to gravity. In more detail, you do describe dimensionless and dimensional spaces mathematically. And so today we've decided to stay a little bit more conceptual for our viewers instead of going into the math. But really, for the viewers who want the math, I really recommend you go to the book. And Doug is even tell you how, for example, I'm looking here, 4D entangled states are the sum of two bivector spinors. WZ Gauss bosons and neutrinos have emerged from 2D qubit space, how the Higgs boson may be the sum of three entangled states, how Doug sees dark matter, much, much more is in that book. So it's really fascinating for those of us who really want to go deep into your deep reality. So today we're going to start with some basics. Thank you so much for agreeing to this. And we're going to work our way up to this better understanding of your model and what you call our quantum mind. So first of all, because spiritual experiencers have long used words like waves of vibration, frequency, and resonance in their descriptions, let's first have you explain the difference between electromagnetic waves and fields within space-time reality and then beyond space-time, quantum waves and fields. Very different. We often get them confused.
Right, right. So you don't start with a hard question, an easy question, do you?
None of them are easy.
No, but I went through the list and they're all pretty much that I can just talk about them. I didn't have to study for your exams.
Oh, good. I'm so glad.
But the idea here is that everybody's used to that we live in a three-dimensional space. There's time. So we're used to things having volume and things exist inside that framework, right? And that's what a field is. A field literally is points in space-time, and they have a little direction, a little point of either a scalar value or a vector value at each point. So think of it as a magnetic field at each point, okay? Mm-hmm. And so when we think of space-time, you know, they didn't even figure out what fields were 150 years ago. That's relatively new, okay? So just imagine that they thought everything had to be local. They didn't understand what a field was even. So, which is kind of, it's kind of an action at a distance too. You know, you have this electron field or magnetic field, and then it has all these little vectors going away from it, right?
Absolutely.
So that's how most people believe. To put a magnet under iron filings, you can get a vision about what that is, right? And so, and even gravity, they think of it as a bowling ball and a rubber sheet. So it's kind of the same model, that there's a little direction about how much space-time is stretched by mass. Okay, so it's all about space-time, 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 which I'm going to simply say is a metric space. That's what space-time is. It's not something you can grab. They always say, can you put it in a wheelbarrow? You can't put space-time in a wheelbarrow. It doesn't exist. It's just a set of conventions for measuring things. So therefore, it's a metric space, okay? And that metric space is warped by gravity. And that's what that means. That's what gravitation, general relativity, special relativity, and all that is, okay? Is all about warping the metric space. Does it actually warp space-time? No, it warps what we think of as the metric that we associate with space-time, because we're trying to put all these events inside this space-time metric space, okay? So the problem is—
That's a great clarification, by the way.
Yeah, and so the question is, does everything exist inside a space-time metric? And the answer is no. And it's because if you're trying to build a regular computer, there's two parts of the regular computer. There's the hardware, and they have a CPU and a memory and all this stuff. And then you have the program that runs on it, right? And the operating system. So it's this software algorithm side and the hardware side, right? Well, quantum computing is also kind of like that. You have the hardware, which they go, if I do this to this atom, then it's going to produce a quantum state, and then I can program it using this algorithm. So we write software for a quantum computer, just like we do with a classical computer, except it looks more mathematical than it does like a program. Okay. And so the question is, the algorithm that you're writing for regular software, that's really just software. It's bits. It doesn't really exist per se. Same thing with a quantum computing algorithm. It's just a mathematical formula. Okay. And so the question is it doesn't do anything unless you actually have a piece of hardware to run it on. But that abstract mathematical state actually represents formally a mathematical high dimensional space. And so that mathematical high dimensional space is just like computer programs also do this. If you have a lot of parallel programs, you have to map them into processors and stuff like that. Well, if you stack the processors as close as you can to each other, you form this 3D grid. And sometimes you're having something on this processor trying to talk to this processor, and there's not a local connection to it. So they have to use the internet connection to go between them. Well, in quantum computing, the same thing is true. You're trying to do this algorithm, and all of a sudden you say, I have a state in this quantum computer. And guess what? That algorithm says that this piece of state and this piece of state, even though they're far away from each other, look non-local from the normal spacetime the spacetime metric that we do. Okay. So what does that mean? Is that the algorithm for quantum computing is an abstract hyperdimensional space. It's more like thought in the sense that it's more like software. It's software. It's not hardware. It doesn't actually exist. It's just instructions for the computer to do things. Okay. Well, that math represents high dimensional space. And anytime you have an algorithm that's higher dimensional than the physical computer that it's sitting in, then it has these what's called anisotropic behaviors, which is that you can figure out a version of the algorithm where things take longer than they should if they were local. And that's what spooky action at a distance is. Quantum algorithms produce this spooky action at a distance because the algorithm itself represents a hyperdimensional space. And so my insight is that let's look at hyperdimensional spaces. And that's my expertise, is hyperdimensional spaces. And we can talk about what that means if you have another question.
Oh, I definitely want to go deep down that rabbit hole, but I do want to clarify, because you definitely explained to our viewers about electromagnetic waves and fields.
Yep. And that's of normal physics, is that way. Most of our
exactly. All this classical physics is about that. And as you pointed out, it's relatively new. I mean, really, Einstein was busy at work in early 1900s, and
115 years ago.
Maxwell and whatever, right? I mean, it was the early half of that century that a lot of this stuff was first being conceived. But
and so
quantum waves and fields, right?
They call these quantum states, they don't even call them states, they call them probability amplitudes, right? And so
we're going to talk about that pretty soon.
Okay.
But if somebody here, right, because most of, let's say, experiencers, right, and that's who you and I are talking for tonight, is experiencers who are really grappling with a language in order to describe their experience. Right. And so we all know that people use the word like, oh, I so resonate with that. Oh, I'm so in sync. Oh, it's about vibrations, man. It's about higher frequency consciousness. And you have said, technically, it really isn't, because if it's in the quantum arena, and we're going to definitely talk more soon about helping people really understand, like, those things that you mentioned, like superposition of states and
hyperdimensional states,
and things like that. But right now, just if we're using the phrase quantum wave, and I don't know if you ever use a phrase quantum fields, but we really want to make sure they understand the difference, that it's not a classical EM field. So how would you describe it in the simplest language, a quantum wave?
Yeah, well, most of the time when they're talking about a quantum, like a quantum computing, or even like anytime you have a chemical interaction, there is a quantum interaction. And in fact, most molecules won't bind in a binding site. A lot of the stuff that we do for our chemistry and our neurology and biology, there's a chemistry that binding requires a quantum state superposition. They get close enough and they go click. And it would be too slow if they didn't do that. So we're using quantum properties of these states that all of a sudden go click and the molecule binds. Okay, so just realize that that's happening all the time anyhow. But if you can put it in an isolated system like you can with a quantum computer and a quantum algorithm, now you can look at it from a purely almost mathematical perspective. And what they describe that is they don't call it a quantum wave. They use the term quantum field theory. What they're trying to say with quantum field theory is says, look, under all the particles and all the even energy particles, photons and other bosons, what are called bosons. Photon is a kind of boson. It's a thing that doesn't have any mass to it, right? So all the particles, there's two kinds of particles with mass, particles without mass. And they're all, each one of those, there's like 50 of them. Each one of them has its own like substrate in the quantum field theory. It's its own little ripple. And you see these little waves in that. And that's how quantum field theory visualizes all that stuff. So you can see some great videos out there about quantum field theory, okay? But the question is, that already still assumes it's a field inside spacetime. So where does spacetime itself come from? And what is the interaction of those particles? How did the electron know to behave like an electron?
Exactly.
Where is the program for the electron? Is there a little computer off on the side to say, oh, when you do this, you're going to behave like this? If you were simulating an electron, you would actually have to do that. You'd have to write the program for the electron how to behave. And we're going to talk about simulation. So I'm going to keep putting little examples of simulation. So the question is, how is that quantum state, which is really, they call about quantum field theory, what is below the quantum field theory? What is below space-time? And if you take a completely reductionist view, we know that the smallest change that you can increment a black hole is a bit. So that's due to John Wheeler, it from bit, right? And so once you know that it from bit is sort of a starting point, even for physics, you go, well, can we just talk about bits in a real mathematical way more than anybody else has done before?
Well, we're definitely going to pretty soon. Yeah. So I think then maybe the short answer for viewers would be, if you start hearing about quantum waves, it's probably mostly related to how quantum field theorists talk about it.
Yes.
And they're talking about it as each subatomic particle has its own field, and particles are simply excitations in that field.
Perfect. Yeah, it's a great summary.
And I might be reading into this, so correct me if I'm wrong, because we're going to be talking about like the wave function or probability amplitude soon. We're going to work our way towards that. But that's probably the other place where our viewers are going to hear things about quantum waves. It's really talking about a quantum wave function. Would you say maybe that's the mathematical lingo for wave?
Yeah, I'll cut this.
Okay, so then quantum waves, we're going to consider that it's quantum field theory language, and that quantum field theory sees every subatomic particle having its related field, and particles are really simply seen as excitations in that field. So would that kind of be a good summary?
Yeah, well said. Yeah.
Okay, great. So now let's clarify the word vibration, because we often hear, and I think you've talked to me about how vibration is distinct than wave or frequency. Maybe you can help people understand the difference between energy, wave, frequency, and vibration, which could be more fundamental.
Yeah, it turns out that if you have a wave and it's in space-time, you know what I'm saying? That wave has what was a trough and a crest, right? And we think of that as like jump back and forth, right? And so that wave is actually in space-time, and so it has a wavelength. You can look from one trough, from one peak to the other peak, and that's what's considered the wavelength for it. And that's a metric, it's a measure. So anything that has a frequency you say it's a frequency, by definition, you mean it has a wavelength and it has cycles per second, which is time, and a wavelength, which is, how many centimeters the wavelength is. And those are metrics in space and time. So anytime we're talking about frequency, we're talking about a space-time metric. So the question is, what can you talk about that's vibration that is not in space-time?
Exactly.
Okay. And it turns out quantum field theory is like that. You can actually say, and string theory is more like that. And where essentially you have this abstract mathematical thing that's vibrating, but it has no sense of space to it and no sense of time to it. All it knows is it's either doing one cycle between the two ends or two cycles between the two ends, or it's forming this knot and loop. And so it has this fancy recursive structure that's talking to itself and vibrating. So that's a vibration. So that is more primitive than anything we see as frequency in space-time. So I always like to use the word vibration instead of frequency.
That's a great distinction. Yeah,
Okay.
really great distinction.
And, and one of the things that people do is they say, well, the chakras are different frequencies. Now it's because we visualize them with colors, the red, orange, yellow, green, blue. And they say, as we go up the chakras, right, that they're more higher frequency, so they must be more better or something like that, okay? But again, those are abstract qualities we attach to those chakras, and psychics see them, and so they attribute those colors to them. But I like to think of the chakras as being, as they're going up, they show them as lotus petals, right? And the lotus petals, the ones near the top, are much higher, have more lotus petals in them. So it's not that it's higher frequency, it's more complex. So I like higher complexity rather than higher frequency for the chakras.
Well, and the chakras are going to get really complicated too. I think it was Valerie Hunt who did some experimental work with the clairvoyant Rosalind Bruyere.
Yeah.
And basically, I think they would have a subject, let's say, sit down, and Rosalind would be noting what colors was she seeing in the person's aura in various chakra areas. And then Valerie Hunt had equipment and was measuring. And in her book, I think it was called Infinite Mind, perhaps, but she was kind of showing how electromagnetically she could validate the frequency bandwidth according to the colors that Rosalind said that she was seeing. But as you're mentioning, there's other things going on besides electromagnetism. So auras.
So let's talk about that, because you've historically said that frequency is energy. I mean, energy is information. Well, energy can be carried on. I mean, one way to ship people information is on the internet. You can ship bits on the internet, right? A file, right? You can mail it to them, right? That's bits. But you can also put the file on a disk drive and mail them the disk drive. So you're not using energy. You're using energy encoded on a disk. You're using mass encoded energy instead of just pure energy on the internet, electromagnetics, to get information. And I say that you can also have information that's not encoded in either mass or energy.
And that's where we're headed next, when we really getting into telling people about your bit physics. Now,
bit physics, geometric algebra.
Yes. Now, first, you use the phrase quantum mind, right? So we've helped the viewers understand space-time involving electromagnetism, energy, mass, by frequencies.
Space-time.
Exactly. And
those are all metric space terms, and they all have
Exactly.
meanings from a physics and a metric space perspective.
Exactly, right? And then we distinguish it between a little bit of the quantum words. And so you've actually asserted that we have a quantum mind. Thank you, Quantum Doug. I so appreciate that as an experiencer.
Yeah,
and
it's different than a quantum brain, too.
And
very different.
We're going to introduce people to some terms, because quantum, very basically for people where this starts, making their eyeballs roll. Quantum refers to kind of two things, doesn't it? It refers to a quantum, of energy.
Discrete,
We found
accountable
out
set of things. Yeah.
exactly. We used to think things were continuous, and we found no, it comes in these discrete packets. So like
single
a
electron, single photons, those are quanta, not quantum, but quanta
right?
Of primitive particles. Yes.
Exactly. Quantum plural. And so it also refers to special properties that now we call quantum, right? So for example, superposition of states, we've mentioned, non-locality, entanglement. So I'm going to have you differentiate those three terms in particular, because as you and I have talked, it is so easy for a lot of people to get those three terms a little bit misused.
Right, right. And so literally a bit originally came from computer science. It just says all a bit is some minimum way of representing some kind of distinction. That's it, a distinction of some kind. And so the distinction is a two-part distinction: on or off, yes or no, plus or minus, 0 or 1. It's just a distinction, okay? And we have, since that's the minimum amount that you can do distinctions with, now we can build circuit gates that can distinguish between when the voltage is high, that's a 1, and when the voltage is low, that's a 0, and then we can do computation with it. That's how computers are built, okay? So a bit is just a distinction. But in physics now, we know that if you, this is Landauer's principle, which is from 1960s. He was an IBM fellow, and he was basically saying, look, if you're trying to throw some information like a hard drive into a black hole, and you don't account for the fact that you have information stored on that hard drive, or maybe it's just a quantum state, you have a bit stored in the quantum state. Either way, it's information stored in some representation, right? You throw it into a black hole and erase it. Can you just ignore the fact that that bit is there? And he could presume no. And he proved that that's called Landauer's principle. And basically every bit has a minimum amount of energy that you have to count for. And the way that they figured out how to talk about that is, imagine each bit is a billiard ball, a wooden billiard ball. Now it turns out you can compute, you can build this little maze, and you can have billiard balls go in, bounce off each other, and come out, and the answer is the position of the billiard ball. So that's called a reversible computer, because you could put them in or out either way. Reversible computing came out of that, okay? And so you don't have to spend any energy, you just have to construct this maze so that you can compute. But the problem is, every time you create a billiard ball, it's like creating a bit, you have to turn the sawdust into a ball. It takes energy to do that, manufacturing. And then every time you want to get rid of a billiard ball, you have to crush it into sawdust again. Down on the bottom here is the sawdust of building and destroying. So the sawdust is the energy. It's the energy of creating bits and destroying bits. That's the metaphor that he used, okay? And so once you realize that even information has an effective energy.
Okay.
It has an effective energy, yeah, which is erasing that. You have to account from an entropy perspective, from a thermodynamics perspective. You can't just say, oh, I don't have to worry about that, right? I can just ignore that. No, you can't.
So it's in that way that it's physical.
Yeah, that's why he called it information is physical. That was his theory, Landauer's principle, okay? And so the question is, if you have information and you know it's physical, in the laws of physics, you have to account for it to make it all sense. Then they showed from John Wheeler showed that if you throw a quantum state into a black hole, you have to account for that bit. In fact, that bit shows up as the minimum surface area of a black hole, Planck's area on the side. So a bit, the surface area of a black hole is bits. And it shows this globe, this black hole with little bits on all the surface, okay, on it. And so that's what a black hole, it's really a bit bucket. And all the mass is on its surface area as bits. It's called spaghettification. It's easy for me to say.
Yeah, that is the hardest word.
Spaghettification, it says it turns all matter, all energy into bits, and its surface area on the black hole. And so once physics have known about this for 30, 40 years already, okay, and black hole mechanics requires this to be true in order for black holes to work like we expect them to. Okay, so it has nothing to do with relativity. It has to do with integrating information theory, quantum theory, and black holes, which includes Landauer's principle. Okay, and that's all tied together now. So you can't just learn part of physics. You have to learn it all together to make it all sense. So
Well, that's the
hopefully
trouble. I think that's why a lot of people don't try. But now
Well,
here
yeah.
we are trying to help people understand why you use the phrase
Bits.
quantum
These are-
mind,
Yeah, okay.
right?
So
Quantum
these are
mind.
bits. Right.
Okay.
And so I did finish your original question, was if you have a bit, what's that? A bit. So we have a more physical definition of a bit now. Okay. And so you can mathematics, just like remember you're talking about hardware versus software, you can actually mathematically represent this bit like they historically do with zeros and ones. But I found it much better to use an algebra instead of Boolean algebra, to use a thing that has more related to physics, a geometric algebra. And that was the math I used for my PhD back 22 years ago. Okay. And geometric
you said
algebra,
you used it because it was actually more related to physics.
yeah, because now you can integrate bits in math and computer science with physics. And so that's what my book is trying to do, and a lot of my lectures talk about, is if you have a bit and it's literally a little, instead of just a little slot in on your desk that you have either coin heads or tails in, that's considered a bit too, right? A coin, either heads or tails, that's a bit. No, we actually have a vector, and the little vector is a little vector that's pointing up or down, and that's the 1 or 0. It's plus 1 or minus 1, right? Plus or minus, right? And so now you have this mathematical representation. And if you have 2 of those, you can form a qubit. So what does that mean? You have 2 dimensions like this, and they're orthogonal, which means they're 90 degrees apart. And now, anytime you know anything about dimensionality, you can go north and south without going east and west. They're independent. That's what physics is all about, these mathematical ways of expressing independence, degrees of freedom, okay? So we've done that now at the lowest possible way. We have a vector that says, here's a vector space that has 2 dimensions in it, and guess what? We can go not only north or east, but we can also go northeast. We can go at a 45-degree angle. That's superposition. Superposition, it says you're not on one axis or the other, you're now 45-degree angle or 30-degree angle or 70-degree angle, whatever. And that's this quantum state that we now call a phase angle in a qubit. Okay. And you can say, well, that's not in a quantum computer, but mathematically it represents what's in the quantum computer. And we know that this is true because light is polarized. Left, vertical and horizontal polarization can be mathematically represented as a qubit state. And it has phase angle.
Okay, so let me make sure I'm following you. And as you're describing the bits, and as you're describing in terms of vectors, let's say, you're describing it in terms of dimensions. So you're explaining how you see dimensions. So for experiencers who talk about a multidimensional reality or wondering about a multiverse and what have you, here you are explaining how you conceive dimensions, and that
the raw
material, and that is the precursor for understanding the original question around what is really superposition and superposition of states. So so would there be a simple way to describe something that's a superposition of states?
Yes. For example, a lot of people think about happy, and then they think that there's the opposite of happy. I mean, if you asked 100 people what's the opposite of happy, they would come up with 50 different answers.
True.
Right? because one would be happy and sad, the other one would be happy and angry, and the other one would be happy and depressed. It turns out there's a happy dimension. Think of it as a bit dimension. Right. And there's the happy and not happy. But you don't know if it's not happy, it could be something else. So let's say we're going to be sad as another dimension. So we can have sad and not sad. Essentially it's a dimension that has its 2 ends of it. It's like a dimension
of sadness.
Yes. Yes. And
a dimension of happiness.
So now you know.
Of anger.
Yes. And so now you know.
It can be all of those at the same time.
Yes. If you have happy, sad, if you've ever been in happy, sad, now you know you're at a 45. That's a superposition. So anytime you take any basic emotion, it turns out, they're all 90 degrees from each other. And you can have any mixture of them as you want, including Republican and Democrat, and happy and sad, and, you know, tired and excited at the same time. You know, you can have all those dimensions. So, and each of those dimensions have meaning, if you want to think about it. So this is the beginning of a meaning algebra, or meaning.
We're definitely going to go deeper on that later.
Yeah, exactly. So, so there was a simpler example, and
Love
it's
that
an
example.
exact metaphor for what happens. Maybe dimensions, maybe happiness isn't a primitive dimension, but maybe you can have a bigger version of that called, call it thought vector, which is if you have a whole bunch of these dimensions, all the attributes that would go into happy form this big thought vector, and it has exactly the same properties. It has superposition, it has the inversion. And so if anyone ever tells you polarity, opposite, and they give you a different label for the opposite, don't agree with them, because every thought is its own orthogonal dimension with its own meaning, and now you can mix them arbitrarily.
I love that. I think that's the best explanation for superposition that I've actually ever heard of. And
yes,
I think for our viewers, you really helped paint a picture of how you're conceiving of a quantum mind.
And superposition too, yeah.
And the fact that we can have a superposition of states.
Yeah.
You hinted at how bits can be constructed and structured to create more complex emotions and thoughts.
Yeah.
So you've definitely paved the way for that. And now
we didn't talk about E-bits yet.
Yeah.
So if you want to talk about E-bits.
Because I was going to say, now let's take it to non-locality entanglement, making sure they clarify those.
That's the next.
Yeah, qubits and E-bits.
So if you are in, you know, this is X and Y coordinates, X and Y coordinates. This is a single qubit. And my PhD showed you that you can do a qubit, which is 2 bits. And it exactly matches all the things we know about qubits using a different math. I hated the math that they did for Hilbert space math because it had complex numbers in it. And I said, I don't need that. And then I figured out that this other math worked just as well. And that's what I showed for my PhD, that you have all the states of the quantum qubit in this different kind of math. And guess what? It doesn't have complex numbers. It only has real numbers in it.
Fantastic.
Okay. So if you have this dimension space here and this dimension, you have 2 qubits now, and you combine them. This is what an E-bit is.
Which stands for entangled bit, right?
Yeah, that's a short term for entanglement. Now, let's say this is a quantum computing, but imagine that you had 2 photons that were in a superposition, each one in their own superposition, or 2 microtubulins, you know, in a microtubule. They each had a quantum state. So this is a mathematical abstraction of the quantum state, 2 qubits, okay? If you put them together, you call that coupling. It just means that the quantum states can interact. And when that happens, you don't just have 4, you have 4, but it's not like it's not this one, this one, this one, and this one. It's all the permutations of it. It's this one and this one, this one and this one, like that. It's all the permutations. So, and they label them as 0, 0, 1, 0, 0, 1, 1, 0, and 1, 1. I mean, it's just a label for this new dimension, which is a combination of 2 other dimensions.
So it's really like taking 2 pairs.
Yes, and combining them.
And combining them mathematically.
All the permutations.
All the permutations. Got it. Okay.
And this is
that becomes an entangled bit.
Quantum computing. This is the exponential power of quantum computing. And of all quantum superposition. Quantum superposition is not only quantum superposition of each qubit, but the new coupled state of a quantum register. It just means these quantum states are interacting. And I don't have to say anything more about them than that they're interacting, like in a microtubule, for example.
Yes, and someone trying to understand the quantum mind, with what you said, it gets everyone's mind thinking of all the ways that mind and emotion is complex, the way consciousness is complex, and therefore how complex all these E-bits, entangled bits can get.
And it's exponential growth. So if I have 2 of these,
Yes.
bits, I get 4 states. You go, that's no big deal. But if I have 3 of them, right, then you have 8. You have 2 to the n, where n is the number of qubits, or q is the number of qubits.
Mm-hmm.
So for 2 qubits, you have 4. For 3 qubits, you have 8. For 4 qubits, you have 16 states. But you have all the states, 0, 0, 0, 0, like for 3 of them, 0, 0, 0, 0, 0, 1. We're just counting them. We're enumerating all the 8 versions of them, right?
Right.
And if you have a qubit quantum register that's coupled, you now have 2 to the q states. And if you have a 300 qubit quantum register, you have 2 to the 300th quantum states all there in superposition at one time. And that just means they're all there concurrently. They're not individually. If you have a regular computer register, you can only have one value in there. But in a quantum superposition in coupled register, you have 2 to the n states simultaneously present.
Concurrent.
And 2 to the 300 is so big, it's more than the number of known primitive particles in the universe, 2 to the 300. That's the
amazing
power of quantum computing and quantum mind. So we're much smarter, the fact that we have a quantum mind, than if we have a classical brain or classical computer mind. So.
Oh, exactly. And so when it comes to the word non-locality, then how would you like people
That's
to
the
understand
next step.
that word?
So,
yeah.
So if you have all the permutations of 2 qubits, you end up with 4 of these states. Well, if you cancel out 2 of those, you end up with something that looks like this. And I've got some pictures of these sometimes. I'll show you an example. I'll just.
And I'm going to make sure that it says multiple participants can show, so you can show screen at any time.
There you go. Thank you. So I'm going to share my screen, and I'm going to put a screen here. And I'm going to bring up my PowerPoint. And this is the one here.
Oh, I love that slide.
Yeah, this is what we're talking about is and I knew this, you wanted me to bring this up. And we're talking about everything below the blue line here. So, and what we're going to talk about is this E-bits. I'm going to show you a better picture of what I mean by an E-bit here. Okay.
Great.
And so if you take 2 of these qubits, I'm not just going to present, I'm just going to show you here. If you take this qubit here with 2 dimensions, this qubit here, and you produce 2 of those, you combine them, normally you would get all 4 combinations. But if you apply what's called the Bell operator to this, 2 of them disappear. This here is a state that looks just like a qubit, but it's a higher dimensional version of a qubit. That's an E-bit. And this here is a single state that represents something that's separated but acting as one. So it's a wholeness thing. And that's where spooky action at a distance comes. It comes from the hyperdimensional math associated with this complex 4-dimensional object, where if you measure this, you get something that looks like 0, 0, 1, 1. If you measure 1, the other one is the same, whereas the other one's the opposite. So this is what's called Bell operator in Bell state. And the math that I did for my PhD shows the same thing. So when we're talking about entanglement, we're talking about this E-bits, which is really a 4-dimensional thing. Now you say, spooky action at distance. What does that mean? I'm going to stop sharing here. Spooky action at distance. What does that mean? It just means we're trying to wrap our head around as if it's 3-dimensional when it's really a 4-dimensional thing. So it has a back door. And it's not electromagnetic either. It's its own primitive dimension that's its own back door. And you put each of the 2 sides of the E-bit in lead barriers that are a mile long, and you say, I'm going to block that quantum state. No, you can't, because it's cheating. It's using its own private dimensions to do it. So when we talk about, anytime you say entangled, most people mean E-bits. They don't mean coupled registers. They don't just mean large superposition of states. They don't usually mean it. Usually if they're using entangled, they mean E-bits. And
well, let me give you the example I hear most. Let me give you the example I hear most often, so that then you can translate the language. Because for us lay people who are reading quantum physics, the examples that we hear most often are, let's say, entangled photons, right? And now I'm going to use loose language for people less technical even than I like to go. But if we tickle the sibling photon that's now in London, the sibling photon that's in California laughs at the exact same time. So there appears to be spooky action in the distance. There appears to be this simultaneous connection where when one is affected, the other is exactly affected at the same time. It might be in an opposite way, an opposite spin.
Yeah, it's going to either be this complementary or anti-complementary.
Yeah. And so, like you said, on one hand, no wonder it gets confused, because if you hear spooky action at a distance, you're usually thinking of the word entangled, because entangled, we usually think, well, most people don't even think of the word EBITs.
Yeah,
but
it's just a short version of that. Yeah.
Yeah, because I think most people are writing about it in terms of like entangled particles, entangled photons. They aren't really even speaking the bit language that you're introducing us to.
Yes, right. So one of the things I wanted to point out is in order, if you just couple two qubits together, you don't get an entangled state. You get a coupled state. You get a superposition of all the states. All a superposition means it's all of those states simultaneously.
It's heads and tails.
Yeah, it's all of them. It's there. They're all permutations are there. The exponential growth of state space that we talked about, 2 to the 300 or whatever the number of qubits is. But when you apply a specific operator to that register, then a bunch of those disappear, so that just this complementary state is in there. And that's what an EBIT is. And so it turns out anytime they're doing Alice and Bob kind of language in quantum computing descriptions, and they're using it to do quantum key distribution or any other kind of things, most of the time they're not talking about superposition, they're talking about entanglement. And
yes, that's when I normally hear the Alice and Bob. It's about entanglement. It's about the fact that as soon as you measure Bob, you're going to know Alice.
Yes, but you can't use it to send any information because they both look random. It's just they're opposite of each other. You only can find out the statistics about the entanglement result of the measurement is if you look at both ends. Well, then it doesn't help to have a non-local connection. You can only do it in the laboratory. You say, this is what I got, and I know that the state that I got the answer faster than the speed of light could get between these two. They've done hundreds of kilometers separated between the two EBITs. And that's what quantum key distribution is all about, quantum entanglement, even through free space. The Chinese are doing entangled state space, quantum key distribution for secure communications between their satellites and Earth through free space. So you don't have to have.
Let's face it, quantum, the computing industry really is the most prolific use of quantum that we know, and that's what's so special about you, is because you have this esoteric side to you, this side of you that loves to go deep down the rabbit hole that experiencers have. And you're not just about shut up and calculate. You're not just about quantum, computing. Now, so if I use the word entanglement, I'm pretty confident that I usually use the word correctly. You make me want.
I think you do.
You make me want to ask you, when would I use the word non-local instead of entanglement?
If you use both of them synonymously most of the time, it just depends on what you're talking about. If you're talking about, I'm trying to see the result of the computation far away from where the other one. See, most of the time, these quantum registers are right near each other. So there's no separation of the two halves. And by the way, the only way you can make this entangled state is applying the quote Bell operator, right? Well, how do they do that with photons? They have a special crystal that they hit it with a high energy photon, and it creates two entangled photons. You can't just take two photons and entangle them. It doesn't work that way. You have to create it specially by creating a pair of photons, by breaking it down by the high energy photon hits the lattice of this crystal and produces two photons that are lower energy that are now entangled. And that's how these EBIT generators are used. I'm actually manufactured. You have to go buy one of these.
Thank you for that. That's a great, simple explanation of how does one entangle a photon. A side question then, I've heard in recent experiments, they can, something like a photon entangled with itself.
Well, lot of people use the word entanglement when they really mean,
Interference patterns.
yeah, that they're cooperating, you know. And so, for example, a laser is really not entangled. It's taking all, it's because of the physical structure of the crystal in the laser, the original, that, you know, they had basically a half mirrored, fully mirrored and a half mirrored structure, and they would get these photons generated and they would start bouncing back. And because of the length of the crystal, all these atoms would be exactly the same wavelength, and they would all be exactly the same wavelength, and they would be coherent. And since they were all like soldiers marching, so people talk about coherence in lasers like that. Like heart math also talks about coherence. They say heart and mind. So think of it as everybody acting as a whole. So if you hear the word coherence by itself, think it's everything acting as a whole, and that's a common definition. Some coherence, like a laser, means that they're all acting as a whole, but they're all marching like soldiers, all lined up. That's a special kind of coherence.
Yes, and I'm glad that you're bringing that up because, like you said, a lot of our viewers probably are familiar with heart math. And so
heart brain coherence, acting as a whole. Again, acting as a whole seems like a reasonable definition for that.
Yes, well, and a lot of times in, let's say, bioenergetic literature, when they're really talking about, let's say, quantum biologists are talking, and they're talking about biological structures and the energies associated with that. So like you said, they're usually talking about electromagnetic energy. They're talking about two waves that end up resonating, so they're in sync. Waves, like you said, peaks and troughs are lined up. And
but
then
light, but light doesn't interact with itself at all.
Interesting, right? So in that case, they're talking about waves that get in sync, and then they call that resonance. And then they say once it starts resonating, this beautiful thing happens where information from the one affects the other. They have mutual vibratory effects on one another is the language that's often used. And then, like you said, coherence like a laser. So when you were just talking about the coupling of qubits, or was it coupling of e-bits?
Coupling of qubits makes the beginning of the register that contains the states, and then if you apply the Bell operator to it, then you get the e-bit. Okay,
then you get the
you can do that in quantum computer. A quantum computer, you can apply the Bell operator to it. Yeah. So.
Oh, beautiful. Okay, that is, that's fantastic then.
But light doesn't interact with itself at all, except if you interfere with itself. It doesn't interact, but it interacts with the measurement device, because when one is going up, the other one's going down, and that's an interference pattern. It's not interacting with itself. It's just that from the perspective of the measurement device, there's nothing there.
Yeah, and I'd have to go and look at what that headline was I recently read.
Yeah.
And,
so just realize that interference with light is really hard. And by the way, interference with quantum superposition is also hard, but it's because most of the time we're not used to thinking about parallel computing, but quantum computing is exponential parallel computing. That's why I'm saying our mind is probably a quantum computer, because we're exponentially smarter, and we wouldn't have survived from a survival perspective, from an evolutionary perspective, if our mind wasn't a quantum computer, because we were too dumb to have survived otherwise.
I love that. Okay, I think you have maybe prepared us for this next question. Okay. Again, we're building up to better understanding. And it's going to be about quantum wave probability amplitudes now, right? Because we've talked about superposition of states, and often you will kind of see a bell curve type of situation. And it's like, okay, we have a superposition of particles. And oh, by the way, when we measure, it goes from all states to one state. And we'll talk about that later. Yeah. But most of us don't really, let's face it, understand that superposition of states in terms of these probability, quantum wave probability amplitudes. So I'm looking at
you want me to talk about that a little bit?
Yeah, I do, because it said, I think you said somewhere here in research that mind appears to directly affect the physical world through information changes in quantum wave probability amplitudes. and that shows up as changes in order or disorder of the system, which was a very helpful explanation. So
Right.
with that, yeah, can you help us understand?
Yeah,
that?
well, Dean Radin, he did this double slit experiment that was completely enclosed and self-contained and in a electromagnetically sealed box, right? And it was automatically sending a double slit experiment, and he was measuring the result of the double slit, and you would expect this distribution, this wave-like property. And when people were putting their attention on it, this is just a kind of automated PK device, okay, psychokinesis device. And so, and he did this perfectly great, and he did the analysis on it, and then he had all these people on the internet try to connect with it. So you could run an experiment over the internet and say, focus in on this and try to change it. And then he would get all the results. And he would show that just with when they were relaxing and not intending to change it versus when they were intending, that the probability that these wave peak troughs that would be showing up on the detector would change. So they were affecting essentially the quantum probabilities that they were going through these two double slits. And so, by the way, there is no known mechanism for directly affecting a quantum state in that kind of environment. The way a quantum computer does it is using microwaves and all this other stuff to change. And it's not just a double slit. It's actually going in and doing stuff where microwaves affects it, to do that. Okay. So it's a brilliant experiment. And he got the results that you'd expect. And it basically says, look, the mind can directly affect quantum states. So if you believe that, you say, how is that possible? And I believe that is because our mind is the same mechanism, the source science perspective, as quantum states. They're the same thing. That's why we can interact with it. So think of it as, I like to call it
that makes total sense to me.
Our mind is the source code, if you want to think about it as an algorithm running the universe. Our mind is the source code that can interact with the computer running the universe. So we're the algorithm, affecting the computer that's running the universe, which is all quantum field theory and all quantum minds, which affects not only microtubules collapse. I mean, anytime you can change a quantum state, you can cause it to collapse. This quote observer effect, right? You don't need a human observer, but if you do a measurement, you're collapsing it, right? And we do that all the time. Let's say we're trying to make a decision about something. And what that is it's a quantum superposition of all the probabilities of all the possible things that you're doing in making this decision. And you're balancing them all at once at one time. And then it's sitting here like this big superposition of states, which are the probabilities of all your decisions. And you're putting a little attention, without collapsing the wave function, you're paying attention to which part of that wave function you're looking at in your mind. And then all of a sudden you make a decision and the whole thing collapses, and now all of those probabilities are gone. You can look at it historically and say, well, I thought about all those probabilities, but you actually made a decision. You collapse those probabilities into a single future, if you want to think about it. So what we actually do is do that with our decision making.
Yeah, I love that. That's a really great example.
And healers can see those quantum probabilities in your mind. I know a lady who can do that. I talk about it in the book.
Does she
can see
elaborate?
all of that probabilities in the mind, and she can go say, she doesn't tell them sometimes, these people, this, but she says, all you have to do is change. It's like, just pull this little stick out here and the whole thing will collapse. Because they're kind of like creating all this complexity and they're not letting it collapse.
Yes.
So
yes, I can feel into what you're saying. Does she elaborate how she sees the superposition of states?
Well, one of the picture in the book that shows that actually shows the aura, the color aura picture. It's not color in the book, it's black and white, but that picture is her picture. So she sees these thoughts as probabilities, waves, probability clouds.
Hold on, I have to see if I just heard you right. So there was some pictures of people, dogs, and what have you. Is she saying that when she sees the aura, she's actually seeing it as a probability cloud?
She's saying that when she's was doing therapy with clients.
Yeah.
And she it wasn't the one with the auras with the dogs. That was my sister.
Oh, okay.
But another picture that showed the aura, when I'm talking about the chakras and the aura, there's a picture that shows this big cloud of a normal aura like picture, you know. And she had it drawn, colored, and she gave me permission to use it in the book. Of course, it's black and white, but
Yeah.
She
Interesting.
sees auras that way, the typical way you'd expect it to, right? But she sees that as information clouds, as probability clouds, where people are balancing all of these information fields and trying to make decisions about things. So
Now, what you just said is this beautiful setup for our lay people brains to really now grasp why, when a psychic tries to predict, quote, quote, the future, I've had other researchers say it's not so much that they're usually wrong, the good ones. It's the time might be off because we're still such a part of the entire math, if you will, that any of us in our decisions and what we do every moment is still computing into
it's this
probability
set of probabilities
cloud.
that are in superposition. They haven't collapsed yet.
Exactly.
You can think of that as a quantum cloud or a quantum mind cloud or whatever.
Beautiful. Yeah. So no wonder that someone might truly be a talented psychic, might truly get a precognitive sense of something that's about ready to happen. And no wonder that it can affect a little bit of the timing or the space of it, just because of all it's still active.
Yeah.
It's active.
Yeah, and it hasn't necessarily collapsed yet.
Yeah, and that's
and it's outside of time.
Exactly. Oh, I love that. And no wonder that you know, there's a lot of people who are scared right now because there's so many, you know, gloom and doom catastrophic scenarios being thrown out there. And especially I'm hearing of a lot of young people who are quite freaked out. So I hope that some of this information gets to them and they can understand that we are not powerless. And this is exactly why, as you and I talk about the individual mind that is quantum, apart from the brain, we are a collective mind. We are all working as a superposition of states. And each of our individual decisions are collapsing certain parts.
Yeah, sub parts of the domain. Yeah,
but like you said,
it's not a field.
But it's not a field,
and it's not in space-time. It's an informational cloud, like informational cloud, and we can think of it as a probability cloud, which is more like quantum computing states as probabilities than anything else.
But I love those both phrases, you know, calling it an information cloud and calling it a probability cloud, I think is a great way to word it for us to grasp. But it shows the power that we have, doesn't it?
Yeah.
It says
we're not powerless.
That future is not set in stone. And each action that we take independently, definitely our part is important to the whole.
Free will.
We have free will, absolutely.
Yeah.
Anything more you want to say about free will?
Well, just remember, probability and information are related.
Yeah.
If you were to look at all these probabilities and then you were to measure it 100 times, you would find out that these probability states are more likely than not, and that's the information stored in the probabilities. So that's what quantum computing does. The actual quantum states are, quote, probability amplitudes. They're just a mathematical way of representing that something that if you square it, you get the probability. So quantum states, quantum computing is all about probabilities, and they call this wave function, this algorithmic mathematical algorithm that they use for talking about quantum computing, as a set of these probability amplitudes. And those probability amplitudes are just all anchors on a radius of one in the quantum state world. So. And
I think I also hear that where the wave amplitude is highest has the greatest likelihood. That is indicative.
Its square is a probability of one.
The greatest probability.
Its square is a probability. So.
Yeah. Oh, that's great.